good morning or good evening if you are in America or other places. Okay, it's my first thanks to the organizer, and especially thanks Dr. Sanjay for inviting me to give a talk. My name is Chongjun Xu from the Complete Genomics. Currently, I'm in the United States. This Complete Genomics is a subsidiary of the MGI Tech. The talk of today is I'm trying to introducing you application of the DNB-based null array, the profiling different types of protein DNA interactions, and the exo, and use this DNB-based null array to do the exo-3 activity assay. And I'm going to talk these several points in introducing the DNB-based null array, and also use the DNB-based null array to do the motif findings. And we call the DOC DocMF. It's DocMF detecting the cleavage site of the switching enzymes, and using the DocFM to testing the CRISPR SP case 9, the switching cleavage site of the latter one, the PAM site, and as well as using the DNB-based null array to do the X3 activity. At first, that's me introducing what is DNB-based null arrays. And the DNB-based null array is a component in the DNA sequencing kits developed by the MGI Tech. We are using the one called the DNB-seq. Basically, this sequence technology is after we purify the double-stranded DNA, we need to make this DNA into a circular single-stranded DNA format, make them circularized. This is single-stranded DNA circularized. Then we are using the rolling circle amplification catalyzed by the 529 polymerase, then form a DNB. This is a DNA nullibles. These are single-stranded DNAs. This single-stranded DNA has 100 to 1,000 copies of the circular single-stranded DNA. Then this one we call the DNB, actually single-stranded DNA template. We load this one into the floor cell, which is this one here. And this floor cell is designed at the way like each binding site only can attach one DNB. Therefore, we have a lot of DNB touch the floor cells. Then we do the DNB sequencing. In BGI, we have developed several different kinds of DNA sequencer. We call the BGI-seq 500, BGI-seq T400, BGI-seq T50, and the BGI-seq T7. Each of the different kinds of DNA sequencer, we're using different kinds of the floor cell, also called the null arrays. We have, for example, BGI-seq 500, we have 1.8 billion different DNBs loading on this floor cell. We have two triplets there. And for example, T7, we have very high throughput. We have a 7.3 billion DNBs, individual DNBs loading on the chip like that. So the DNB-based array, we are talking about this chip. So basically, then we're trying to introducing the DNB-based on-chip motif finding, which is a DocMF. This is the technologies we developed to checking the interactions between protein and DNA. Basically, for example, the interaction between the protein and DNA, we can be classified into two kinds. One of them is just the bindings, such as the transcription factor binding to the DNA. This binding, then perform of course, they have some specific binding site for it. For example, Tata boxes. And other kinds of, this kind of DNA interaction is no cleavage, just bindings. Another kinds of the DNA protein interaction, just like the restriction enzymes. After the enzymes binding to the DNA, then they will cut the DNA off. So basically, the goal here is we're trying to using DocFM, trying to identify the binding site, the cleavage site, and the binding site for these cases with other cleavage. The way we are doing is like this. We prepare a double-stranded DNA in the DNBs. As we just talked about the DNB, the array on the different DNA on the floor cell is a single-stranded DNAs, which is the DNBs. And the first, then we are doing the sequencing, for example, 100 cycle of using our sequencer to do 100-cycle sequencing. In that sense, we will know each particular DNB, what the sequencing is. But in this case, it is a double-stranded DNA because we have a sequence strand over here already. But because of this sequencing strand, we were introducing some not the native DNA layer. So we call the new synthesis strand has some scars. These are one possibly where alter our interaction abilities between DNA and the proteins. So we are after we know the sequences, we remove this synthesis strand with format. Then the DNA over here, DNB over the floor cell has the single strand against. Then we can sequencing again with the native, we call the code DNTP, which means the DNTP, the base is not modified. When we do the sequencing, we base have to be modified with a fluorescent fluoropher. But in this case, we are sequencing them again. The base is not modified. In this case, we will have double-stranded DNA in the DNB. All of them has a sequencing, but all of them is native DNAs. But now in this case, we have the no sequences. So when we do the protein cleavages, then we just do one cycle. So adding since this one we already knew the sequences, so we're adding one more cycles. We do the images. Then we incubation with our test this For example, this case is restriction enzymes. We'll do the image again. So clearly, if these enzymes, this particular DNB containing the restriction enzyme regulation site, they will be cleaved. Therefore, have no signals. The one without the in the recognition site, they will have the signals not change it. Then we can just the image 1 divided by image 2. If larger some threshold, we can analyze this in DNB, find some features layers. And also, when we are talking about the protein bindings, we can do something like a second strand synthesis. Basically, after we do the double strand DNA, then we are incubation with our test. After we got the signals to 61 more cycles, we got the signals. Then we are incubation of test proteins, basically of the proteins binding there. Then we are doing something like MDA reactions, the one we used for sequencing the second strands. Basically, typically, if the no protein is binding to the DNBs, this is where we were generating second strand. We will have the sequencing signal for the second strands. Then, if we are doing if some proteins binding to the DNBs, binding to TNTP, therefore this one we're not generating good second strands. So this one will be identified by the image 1 versus image 2 intensities. So just for example, this is one of the example of the restriction enzymes. So we are using one of the restriction enzyme as a proof of concept. We are adding the MIU1. So basically, this is a restriction cleavage side of the MIU1, and we got about 500 million DNBs. We got when we do the image 1 versus image 2 intensities, use this as a threshold. We got the 1.98 million DNB containing these sequences. Because we already know the sequences for all the DNBs, basically, we can analyze the feature. What's the 1.98 million DNB? What's the sequence it is? Then we are doing we divide the latter one into submembers, into all the submembers. We to see. So basically, this is the submember frequency. For example, we have 32 submember has a very high frequency with among these 1.92 million DNBs. So then we can sorting with if we are sorting all the submember, you can see the pattern like that. Basically, the peak here actually means 32 submember. These 32 submember, the frequency actually is like that. These are very high frequencies, but they have very good patterns. These is the patterns. For example, the DNBs containing HGGTA, these sequences, they have a very high frequency. Then clearly from here we can do the bioinformatics analysis. We can deduce the common sequence for these guys, 32 submember containing these sequences. Same thing, same method. We are using analyzing, looking for the CRISPR SP-Cas9, the PAM sequence. We know the CRISPR systems, the when we are using the case 9, it's a three-part side. They have the PAM sequence, which is NGG here. And we also know another kind of CRISPR system is using CPF1 enzymes, and which is the PAM sequence is located in the 5' side. Then the important thing is regulation side, the target sequencing is here. So because of that, we designed some DNB structure containing the target sequences. Then we put the each side has a 15 ends in the 5' side and 15 N in the 15 N in the 3' side and 15 N in the 5' side. Then we are using this library to try to identify what the PAM sequence is. And because we have 500 million reads, roughly for each channel of our chip. These 7 mers only have 16,000 7 mers, all the possibilities. These coverage is about 30,000 X PAM sequence coverage. So PAM because we have both 5' side and 3' side, so we can detect the PAM side simultaneously both 5' and 3' side. Just for examples, and for this case, for example, among the 500 million DNBs of incubation with the SP case 9 for 4 hours, we do another images. We found out that about the 300,000 DNBs with the image 1 intensity divided by image 2 intensity larger than 3. Then analyze the feature of these DNBs. We found 944 7 which is important. Then basically here, like this, and like the one in the blue lines means the 5' side. 5' side, all the 7 has almost equally frequencies. The y-axis is the frequency of the 7. This means that they do not have a PAM sequence in the 5' end. But in the 3' end, we can see the frequency for the 7 is different. If we are using threshold here, we got 144 7, which has a much higher frequency than the others. We analyze the 144 7, we find out that the majority of them is containing the sequence NGG. That's accounted for about 90%. We also, because this is a very high coverage is extremely high, so also found 5.8% is NAG, and also 1.6% is NGA. So basically, with this method, we can not only find the NGG, but also can find those of much less sensitive ones. And then we try to see for the binding site, for the binding, we are testing this one by DCase9. DCase9 is a mutation of Cas9. It has ability to binding to the guide RNA, but it cannot cleavage those. Similar, we do the latter ones, and with this frequency, we can see here 5' end is almost the equal frequency for all the 7. For the 3' side, we can clearly see the 7 is spiking for different locations. And we analyze this spiking one, which has a much higher frequency. We find out that this sequencing is NGGs. It's exactly the same as what we discussed before. This is just a binding without the cleavage. Then I will switch gear to the using the DNB library to analyze the X3 activities. The reason why we are doing that is that we know that X3 is a very important enzyme in our molecular biologists. It's also a very common contaminant in our protein purifications, especially in the E. coli expression systems. And currently, we do have a lot of ways to detect X3 activity, but sometimes sensitivity is not that great. So here, to prove the concept, so first we do know we know that X3 will cleave the double-stranded DNA if the 3' side is recessed. But in this case, since our DNB is a 3' side have the fluorescence label, so we are particular hepatitis 3' labeled, sci-fi labeled primer with our DNB, trying to see we check if all the DNB is hybridized with particular primers. All the DNB are light up. The intensity 520s. After we cleavage with our X3, we found that the intensity go back to the background levels, which only have 100. Means that X3 can cleave the 3-part labeled primer, and then we can do the hybrid again with this primer. We can see the signals come back again. That means that this X3 cleavage does not damage the entire DNB. The DNB of the cleavage is still intact, still have the ability to hybrid with the primer again. Furthermore, we know that DNB has of the sequencing, we have the structures like this. Since we are sequencing, we have some, as we said, some scars left on the base. We also 3-part side is not the free hydroxyl group. It's the 3-part side is blocked by the reversible groups. Okay. In this case, for example, we are doing the first cycle of the fresh lambda array. We got the ESR is 95. These are ESR is the parameters indicating the good or bad of the DNBs. And we also have the ACGT medium intensity is a count of thousands levels. After the 100 cycles sequences, we know the signal intensity slightly reduced. Okay. Then after the latter one, we treated with the X3. We treated with X3. We can see the signal intensity go back to background. Okay, that indicating our X3 and can cleave the DNBs left on the sequence strands. Furthermore, we found out that this X3 cleavage is a fairly specific, such as if we are using the lambda DNA, lambda exonucleus 1, T4PNK, exonucleus P1, all of the others, the before cleavage and after cleavage certainly are the same, but only the exonucleus 3 is a fairly specific. After cleavage is going much lower, and we like the another parameters because intensity is good, but it's absolute number we do not like them very much since different assay, different process kind of have different intensities. We are using a relative number, which is ESRs. I'm sorry, we are using the ESR to representing of the cleavage. ESR means the effective spot rates, means the percentage good DNBs. Basically, we are using this ESR to indicating our X-ray activities because of the nucleus actual digestions, ESR will be reduced since the good DNB will be much less. Then we are developing this scheme because we are trying to use the DNB null arrays. Use the DNB null array means that this DNB null array has been used for sequencing. It's ready for trash out through the ways. So we are developing the assay on this used null cells because the DNB, the flow cell used for the sequencing could be very different. Some of them could be using ACE50, some of them ACE 100 cycles, some of them maybe 400 cycles, some of them is a single strand, some of them is very differently. So that is not easy to control. So basically, we are using these ways. So first, we do the initializations. We are adding the larger amount of the exonucleus 3 to remove all the synthetic strands which already in the used null array. It becomes a fresh DNB, just like a fresh arrays. So then we are using the hybridized our primer to one cycle sequencing, just like this, like that. This one we do the images. We got the ESR1. This one, since this is from the fresh regenerated DNB, so this one ESR number should be very high. Then we are adding the controlled amount of X3 activity. For example, the X3 we need to test it. Then we are doing the image again. So we will get another ESR values. If with the ESR2 divided by ESR1, if this number is higher, means that the amount of X3 added is low or the activity is low. So we will get the indicating this one still remaining there. But if this one activity, if this ratio is lower, means that majority of the synthetic strand has been cleaved. So we are using these. So then we are using the sense. Then we're using testing sensors. We are using the dose responsive curve. We are testing different amount of exos. We found out that the sensitivity. This is the y-axis is the ESR ratio, means the ESR2 divided by ESR1, and we found out that this activity assay is as high as a 0.001 units per mils. This is a dose responsive curve. And we also found out that the use array can be reused five consecutive times. We repeated the same flow cell using again, and find out that reactivity is the same. Is the same. And since the XO3 is in the presence of sometimes the contamination sources. So we try to see if this one has in presence of different proteins such as the PNK at different concentrations, like a reversible transcriptase at 4 milligram per mils, we found out that the activity is not that be affected by the other proteins coexisted. So the sensitivity is also at the 0.01 units per mils. And comparing this activity assay, X-ray activity assay, comparing the other available activity assay, this is the detection limit. We believe the one we have in the DNB array is kind of among the highest activities. So the conclusion is DNB array can be used to Docker FMs. Docker FM is a high throughput platforms. They can study the interactions between protein binding and also the cleavage. They can find the binding motif or cleavage motif within the DNAs. Also, use the DNB array can be used to detect X-ray activities. And thanks. This is my coworker who did this work, and also I thank you for your attention. Thank you.